presentation, Transformer and Inductor Modeling with Comsol Multiphysics. I'm Dexter Johnson, and I'll be moderating this presentation. Before we start our presentation, I would like to mention a few housekeeping items. For those of you who want to know if this session will be archived, the answer is yes. It will be archived and will be available for review within about 24 hours and can be found on www.spectrum.ieee.org/webinar. Once the archived webinar is available, a notification email will be sent to all of you and all of the registrants. Secondly, we encourage questions, and I hope we have time for several, which we'll take at the end of our presentations. As your questions occur, please type them in the box provided on your computer screen on the left-hand side and hit the Submit button. You don't have to wait until the end of the presentation to begin submitting questions. As you look over your screen, you should also see buttons that allow you to enlarge the slides if you so desire. About volume control, if you're listening to the audio portion of this event over your computer speakers and you need to adjust the volume, turn your attention to the speaker icon at the top left of the screen. You may also need to adjust the master volume of your computer system. At the bottom of the slide in front of you are a couple of additional suggestions that will improve your viewing experience, including a resource page with today's presentation. Now I would like to introduce our presenters for today. Magnus Olsson, Product Manager, Electromagnetics, Comsol. Magnus received his PhD in Plasma Physics and Nuclear Fusion from the Royal Institute of Technology in Stockholm, Sweden. Prior to joining Comsol, he worked as a consulting specialist in electromagnetic computations for the Swedish Armed Forces. In 1996, he joined the Comsol team, and since 2001, he has been responsible for the development of Comsol's products for electromagnetic design. And today we have Valerio Marra, Technical Marketing Manager, Comsol. Valerio holds a Bachelor of Science and Master of Science in Nuclear Engineering and received a PhD in Energetic Systems and Fluid Machines Engineering from the University of Bologna, Italy. He joined Comsol in 2008 and has worked in both applications, sales, and marketing. He's currently the Technical Marketing Manager and works out of the Burlington, Massachusetts office. And with that, Valerio, I'll turn it over to you if you'd like to begin.
Thank you very much, Dexter, for your introduction. And hello, everyone. My name is Valerio Marra, and I will be the first speaker for today's webinar. This is today's agenda, and as you can see, we will talk about why modeling is so important and why doing it with a multiphysics approach can allow us to simulate transformers and induction application with real-world precision. And please feel free to ask any question that you might have. During the last part of this webinar, we will have a Q&A session to answer all the questions that will come in. And let's get started then. Why do we simulate? Well, for instance, the most critical decisions are made early in the product development cycle, and getting decisions wrong at the concept stage can be very costly. So simulation will give us a great insight into our new application. And another important stage is also design and optimization. So thanks to modeling, once again, we can reduce the number of physical prototypes, or we can investigate different operating scenarios, even the ones that are dangerous or expensive to set up. So simulation, what is bringing to us is bringing to us the possibilities to consider all design aspects. And then we also have testing and verification. For example, we can integrate modeling with the manufacturing process and quality and product quality assurance. And we might want to investigate how material properties can influence our product, or we might want to understand why and which parts failed under certain operating conditions. So these are all good reasons to simulate our application. And I'm sure then that we all agree that simulation can help us to capture the real-world behavior of our products, and Comsol Multiphysics can model all the physics included. And as you can see, we do it in 4 categories, and I mentioned them in this slide. We do electrical, mechanical, fluid, and chemical simulation. The most important thing is that it's natural for us to handle coupled phenomena because it's written in our DNA. 2 or more physics phenomena can affect each other, and we can model this coupling with no limitation or combination. So this is very important. And of course, being a native multiphysics software, it's also capable of solving single physics applications. So we offer to the designer, to the analyst, one integrated environment. One day we can work with heat transfer, the next day we can work on sludge mechanics, then fluid flow, and so forth. And the interface and the workflow is the same for any type of modeling. So this is another advantage. So as you can see from also this slide, simulating with a multiphysics approach means to be able to consider all the phenomena that are influencing the performances of our product and even bring more mature technology to the next level. And before going ahead and talk about Comsol Multiphysics, its interface and architecture, I just would like to highlight the fact that we have users in all industries, like this one, where 3D simulation are decoupled to an electric circuit simulation, and we're talking about transformer application. And this is our Comsol desktop, the environment that I was mentioning before. We have a sleek, simple-to-use interface where all the modeling steps taken are recorded and can be edited later on if needed. And this is actually happening in the window indicated as a model builder. Then we have, of course, the possibility to input our settings just next to the model builder. And then we can visualize our results in the graphic window. Usability is also of the essence for us. And you don't have, for example, you don't have to remember where that particular boundary condition is. You just click on the physics you're working on, and all the relevant options will be presented to you with a context menu. And this is the Comsol Multiphysics architecture. As you can see, we have different products belonging to different areas. And starting from the left, we have electrical, mechanical, fluid, chemical, multipurpose, and interfacing. And the highlight of today's webinar is electrical, of course. All products can be coupled between them and interface with different CAD formats, packages, and data. And now we'll hand the webinar over to Magnus. Thank you very much.
Okay, thank you, Valerio. So I'm Magnus Olsson, and I will introduce you to the more technical part of this presentation, talking about multiphysics and in transformers and inductors. And in the area of inductive modeling, you find a lot of multiphysics effects. You have high-power devices with substantial resistive and inductive heating. You have, probably for that reason, also the need to cool your device, meaning that you have fluid flow, perhaps cooling using transformer oil, convective cooling. You may experience problems or effects due to thermal expansion that you need to dimension your device for. Your device will for sure be connected also to the external world, which may be described using, for instance, external circuits. We have effects like skin effect. We might have noise and vibration due to magnetostriction and other mechanical couplings. We have capacitive effects, magnetic saturation. So there are lots of effects in the modeling of multiphysics in transformers and inductors. Looking at the next slide, we have an overview of typical devices to be modeled and in what industries those devices may appear. So I have a list here of, for instance, transformers and inductors we mentioned. Also more special applications like Litz wire, a stranded wire for efficient power transfer, utilizing the entire area of a conductor, even at extreme skin effect. We have motors and actuators, generators, sensors. We have electromechanical devices like loudspeakers and transducers. You find all these kind of devices in a wide range of industries. For instance, in the aerospace industry, I think we've all heard about the fact that we have more electrical and electromechanical devices in aeroplanes, causing advantages and, of course, new technical challenges. We find the applications in the auto industry and in the automotive industry. Also there we find a trend towards more electromechanical devices and electronic devices. Then we of course have classical industrial areas like electrical power generation and distribution. Then of course we have the electronics industry, steel and metal industry, and so on. So looking at some of the essentials for the modeling of inductive devices, typically you start by describing your device or application by describing the geometry. And that can be done in Comsol Multiphysics using the built-in CAD engine, but we can also use external CAD programs. We have live link to CAD various CAD interface CAD programs. So there is a variety of possibilities to control the geometry model of the device. Then of course we need to specify material properties and the material distribution in the device, perhaps for laminated devices and other anisotropic or sandwich type materials. We have a material orientation. We might need to specify couplings with other physics. So for instance, couplings with heat transfer, heat conduction. Then we will proceed and we will apply appropriate boundary conditions. What conditions apply on the surfaces of the device? Do we have heat loads? Do we apply voltages, etc.? Then, of course, we have various analysis types. So, for instance, we can study a device, see what's happening in the time domain. We can focus on for sinusoidal excitations, we can focus on one frequency at a time, so doing frequency domain simulations. Sometimes it's most appropriate and interesting to start with a stationary response. For instance, if we have saturation effects in magnetic cores and so on, it's probably a good idea to first do a stationary analysis. Depending on what type of study and analysis you perform, it will take more or less time to solve a model. So starting from the easy part, frequency domain is linear and fairly quick and lightweight to solve. Stationary response with nonlinear materials like static saturation problem can be more demanding and require more iterations to arrive at a self-consistent solution. And eventually, if you have a time domain analysis also with nonlinear effects like dynamic saturation, that's typically more demanding type of analysis. Then, of course, we have an important choice. A lot of people today think that modeling and simulation is all about doing things in 3D because while the real world is, after all, 3D. But there are pros and cons. Modeling in 2D has many important application areas, mainly because it's easy to achieve high numeric precision in 2D. It's easier to draw your geometry. You get quick results and get quick feedback on your changes in your model and your design. Resolving the skin effect at high frequencies can be virtually impossible in 3D, whereas in 2D models one can often afford to resolve skin effect and that way analyze frequency dependency of devices that are not possible to study in full 3D. For instance, if you're modeling coils, you can resolve details, you can resolve individual turns in coils with a large number of turns. On the other hand, 3D is to some extent easier because it's more straightforward to specify the geometry. It's really the full thing. You don't have to worry about representing cross-sections or appropriate cross-sections. You can use 3D CAD, and you typically include 3D effects like end effects that would be neglected in 2D modeling. On the other hand, you might have to live with certain simplifications. You can no longer resolve the skin effect in densely wound coils and wires. It's more demanding to solve. It's difficult to resolve detail. So to a large extent, 2D and 3D modeling is complementary, and that's especially true when it comes to the modeling of inductors and transformers. And in Comsol Multiphysics, you have the option of doing modeling in both 2D and 3D. So you have planar 2D, you have axisymmetric 2D formulation, and you have full 3D formulation. Talking a little bit about the multiphysics approach. At the center of this slide we see the word multiphysics, and that's really the heart of the analysis in Comsol Multiphysics, and it's really the heart of modern engineering design. You have a lot of physics effects which interact, and in the past, you have typically focused on one aspect of these, and very often you start looking at, for instance, only electromagnetic effects, only heat transfer, or only structural effects. But eventually, you probably want to see if the interaction between these different fields are important, and if they will give you a nasty surprise when you build and test your prototype. And with the multiphysics approach, you can model all these phenomena separately, and then you can couple them via the multiphysics engine and see what happens when the electromagnetic fields and currents and voltages generate heat, and the device heats up and is cooled down by convective flows, and we'll see how the electromagnetic properties will be affected by the change in temperature, and how that in turn affects the amount of heating you get. So it's a way of analyzing these aspects sequentially or fully coupled. So that's really the whole idea about multiphysics analysis, to be able to work out these dependencies and eventually get to a self-consistent solution, and a design that stands up against all challenges when it comes to heat generation, structural loads, thermally induced structural loads, etc. Looking back at the product architecture of Comsol and the product suite here, in the left column we find the AC/DC module and the RF module, and those are add-ons to the core simulation package Comsol Multiphysics. AC/DC and RF are typically those packages you use to analyze electromagnetic phenomena. For inductors and transformers, it's mainly the AC/DC module that's relevant. In addition to the AC/DC module, it might be interesting to look at the most common couplings, and I would say the standard type of analysis is that you look at the electromagnetic phenomena coupled to heat transfer. Devices heat up and that change the electromagnetic properties, and you want to see what happens and if your design is good enough for a certain current or voltage load. Other couplings that might be interesting is structural mechanics, where you can have well, direct electromechanical forces due to Lorentz forces on conductors, magnetic forces, etc. But we also have, very importantly, thermally induced forces and stresses in materials. So the coupling is just as much between the heat transfer module as in between AC/DC and the structural mechanics module. CFD is, of course, important as well when it comes to cooling, convective cooling. So those are the most strongly connected modules or components in the product suite here. And for the introductory example, we will use AC/DC module and the heat transfer module. So we're going to run a short demonstration here on how to set up a multiphysics problem involving electromagnetic heating, more specifically induction heating in Comsol Multiphysics. The example is the inductive heating of a billet, of a steel billet. So this is something that's common in the steel industry. The billet is typically preheated in an oven, and then before performing some processing on the billet, you need to top up the heat a bit, reheat it using an electromagnetic induction heater to have full control over the amount of power and heat delivered to the device. And this kind of modeling is done in the frequency domain when it comes to the AC part, and the heat transfer is dealt with as a stationary problem. So this is kind of a frequency domain stationary combination, multiphysics combination. The billet enters the induction coil at a velocity of 1 decimeter per second, and in the model we account for temperature at the inlet, and we account for heat losses through convection and radiation, and not the least also we have heat being transported from, because the AC coil will deposit the heat and its power near the surface of the billet, and that will also be conducted towards the interior of the billet. Here we see some results for 50 Hertz, and we can see the central cross-section of the heat source. And we can also see, as the billet is moving through the coil, we have suppressed the coil here for clarity. And we can see that surface temperature goes down here as a result of losses, surface losses, and also conduction to the interior. So with that said, I'll leave over to the recorded demonstration.
I will now build a billet model in Comsol Multiphysics. It is a 3D model. I need to specify what physics to solve for. Under heat transfer, electromagnetic heating, I find the induction heating interface. I'm going to solve it as a frequency stationary study, meaning that I solve for the magnetic fields in the frequency domain and for heat transfer as a stationary problem. I will now specify the geometry. I have a range of options to specify the geometry. I can import a CAD file. I can use one of the live link interfaces for CAD. I can use primitives or work planes. I will take a shortcut and I will insert the ready-made geometry sequence from a file. The geometry sequence consists of primitives and a Boolean operation. Let's build it. And let's look inside. We see the surrounding air domain, we see the billet, and we see the coil. I will now assign materials to the geometry. I do that by right-clicking the Materials node and I open the Material browser. Under Built-in, I find Air that I add to the model. As the first material, it will by default be assigned to all domains. I will change that later by adding another material in the billet domains. For now, I just want to add a small electrical conductivity of 1 Siemens per meter. This is for numerical stability reasons. Next, I scroll down in the material browser until I find iron, and I add that to the model, and I assign iron to the billet domains. I just need to change one thing in the iron. The relative permeability is high, but the billet is preheated to 1000 degrees Celsius, so it's well above the Curie temperature. So I changed the relative permeability to unity. And I can check the air material is now overridden in the domains of the billet. It is time to set up the details of the physics. By looking under the induction heating node, I find the induction heating model. That is the main equation model for the induction heating interface. It has both the frequency domain magnetic fields equation for the magnetic vector potential and the stationary heat equation. Now I don't want to solve the heat equation in the air and the coil, I just want to solve it in the billet. So by right-clicking and selecting magnetic fields, Ampere's law, I add another equation model with only the electromagnetic equation, and I'll assign that to the coil and to the air block. Going back to the induction heating model, I see now that it's overridden, so it's only valid in the billet. Now the billet is moving upwards, so I will add translational motion as a sub-feature to the induction heating model, and I just need to specify the velocity in the upwards direction to 1 decimeter per second. I will now add current density to the coil domain. I do that by selecting magnetic fields, external current density. I'll assign that to the coil part of the geometry. I will use coordinate expressions to enter a current density of 50 megaamps in the azimuthal direction. Like that. Next, I will need boundary conditions, and I add some boundary conditions for the billet. On the sides of the billet, we have convective losses through convective cooling. So I just need to pick the appropriate boundaries here by left-clicking to select the boundary and right-clicking to store the selection. Okay, that's it. And I need to specify a heat transfer coefficient corresponding to free convection. 5 is a good number. I will add also other boundary conditions on these boundaries, so I'll save the selection to save some clicking. Next boundary condition is radiation loss. So surface to ambient radiation. And now I can just refer to the previously stored selection. And I need to specify the surface emissivity, make that user defined. 0 means a non-emissive boundary, perfectly reflecting boundary, and unity is a black body, so I'll put it in between to 0.5. Both the convective cooling and surface to ambient radiation has an ambient temperature setting, which by default is room temperature, so I leave it at that. I also need boundary conditions at the upper and lower ends of the billet. We have a temperature condition because the billet is preheated to 1000 Celsius. So that's the temperature it enters the domain with. So we'll make that 1000 degrees Celsius. And on the upper end, heat is flowing out with, given by the heat content of the billet and the speed of the billet. So I just specify a simple outflow condition. I am done with the physics and I will proceed to create a mesh. I right-click the mesh node and select free tetrahedral. I set the general size to the predefined coarser mesh. In certain domains I want to have a finer mesh, so I add another size feature and set it to the domain level. I'll start with the upper part of the billet and I will make the maximum element size there 4 centimeters. I will reuse this for the central part of the billet. But there I want to use an even finer mesh size, 2 centimeters. Let's build a mesh, and by suppressing boundaries we can look inside. And this is the mesh I wanted. I'm now almost ready to solve the model. I just need to specify the frequency to solve for. The default is 1 kilohertz, but I rather want 50 hertz. Now I just need to right-click the study node and select compute and wait for the solution. Once the model has solved, we get a default temperature plot. I will maximize that in order to better see what's going on. So now we can see the billet. It enters the domain with the initial temperature of 1000 Celsius. It gets heated up by the coil, and then the temperature is conducted towards the center and lost also to the exterior through convection and radiation. So the surface temperature drops towards the exit.
Okay, so that was the end of the demonstration, and I will just comment on a follow-up that we didn't really show in the demonstration, and that is the question, what happens if you increase the frequency? That will be somewhat a challenge in this model. It will be more difficult to solve because you need a finer mesh to resolve the skin effect. But one way of doing that is to utilize the obvious symmetries, so just using a quarter cross-section, and then we solve for 500 hertz, and we can see that there's more skin effect. We get more heating out in the corners of the billet. So by changing the frequencies one way, we can control the heating profile of the billet. Going to the specific modeling features for this kind of modeling, we have a lot of extra tools and features that we can use that will simplify the modeling. So there are ready-made domain level features for the modeling of coils and to specify currents, to do force calculations, and to model domains extending to infinity using infinite elements. And also boundary level features that can be used to specify excitations and to simplify things. For instance, instead of modeling the interior of a good conductor when you have a tiny skin effect. You can exclude that from the simulation and just apply an impedance boundary condition. So there are some really useful features that you can use to speed up or aid your modeling. Especially when it comes to the coil features, we have, for instance, the multi-turn coil domain, which is a homogenized coil, so it doesn't include skin effect. There is a single-turn coil domain, which is intended for the modeling of solid conductors. So it includes free distribution of the current, so skin effects and vicinity effects can be modeled using the single-turn coil domain. And you can bunch single-turn coils into a coil group, and this is specific for 2D modeling, where you maybe have hundreds of little circuits or geometry elements representing cross-sections of the same conductor going back and forth through the geometry. So that way you can model coils and conductors with a large number of strands in series. When it comes to the meshing, here we illustrate some of the meshing tips. We can use boundary layer meshing to help resolving the skin depth by starting meshing from the boundaries and then adding progressive layers from the boundaries. And that's applicable both in 2D and 3D. So that's a neat trick to more efficiently model devices with the skin effect. So here is one example that is an axisymmetric model of a transformer with a skin effect. And we can see the windings, primary and secondary, and we can also see an outer domain here, which is an iron core that encloses the windings. And the solver allows you to easily perform different types of parameter sweeps. So it can be sweeps over material parameters, sweeps over the frequency as here, or you can sweep, for instance, geometrical parameters for analysis of various geometrical designs. So that's, here we can see how we specify a range of frequencies starting at 0 hertz going up to 50 hertz in this case. So here we see the results at 1 hertz, and we see the current density distribution in the windings here. And we can see that we have some vicinity effect and some distribution here of the current. It's not just a DC case, but the skin effect is not very pronounced. So going up to 50 hertz, we see a dramatic change in the current distribution, and we can see that suddenly we are not utilizing the interior of the conductors very well. So we have most of the current is flowing near the surface of the conductors, and this is of course possible to resolve if you mesh finer near the boundaries, or if you use this boundary layer meshing. Adding circuits to a model is of course of interest, and that's easy to do in Comsol Multiphysics. And there are special coupling elements, so there is a special type of circuit element you can insert in the circuit that represents the finite element model. Apart from that, it's pretty straightforward, typical SPICE standard implementation. where you specify the pins of each component, and that's very much it. So the circuit can be connected to for instance, the coil domain features in multiphysics. And there are also general types of connections where you can specify, for instance, a voltage current relation from a finite element model and hook that up to the circuit's interface. Going from 2D to 3D modeling, I thought I'd show you a quick overview here of the modeling of a single-phase E-core transformer. So we have the iron core, and we have the current and the primary and the secondary are wound around the central leg of the core. And this model is solved as a full nonlinear time domain model. So we perform a full nonlinear time domain analysis at a constant frequency of 50 Hertz. But as we include saturation effects in the core, the model is nonlinear, so you cannot easily use frequency domain modeling. The primary and secondary windings here are modeled as homogenized current carrying domains. So we don't resolve individual wires, so it's a homogenized coil model. The skin effect in the winding and in the core is not included in this particular model. The assumption in the homogenization is that you have a coil with thin wires, so we don't really have to bother too much about skin effect in each wire here. Its wire diameter is much less than the skin depth, and there are many terms. So the coil can be assumed to be a homogeneous carrying domain. So we just spread out the current as a homogeneous current distribution across the cross section of the coil. And looking at the results for the first case here, we have here equal number of turns in the primary and secondary, and so we only have inductive effect, but we have no step up or step down effect of the voltages. And that's really a test where we push the core deeply into saturation, and that can be seen when looking at the results curves here. They are, even though we have a sinusoidal excitation, results are far from sinusoidal. Going one step further here, looking at the current, we can see that, for instance, the current in the primary is more or less a sawtooth rather than a sinusoid. The current in the secondary is a little bit more rounded, but we have also there pretty strong nonlinear effects. And we can look, of course, at the results here at the magnetic flux density distribution. We can look at the direction of the magnetic flux density using arrows or streamlines. Second step here of the analysis is for a different ratio of the windings. So now we are modeling a step-down transformer. And looking at the results now, we're not pushing the iron core into saturation anymore, and we have a step down of the voltage here of the MP to NS ratio of 1000. So that brings us to the end of the presentation, and I'll hand over to Dexter for the Q&A session.
Great. Thank you very much, Magnus. Before we get to our Q&A, I just want to put out a slide with the product suite again with the sort of architecture of Comsol. I'd also like to point out that we have a lot of questions, and the Comsol team will answer, I believe, almost all of them at some point if we don't get to them live today. So the first question I have here is, could the physical deflection of a three-phase copper bus bar configuration with supporting structure due to a bolted fault or given ampacity and duration be determined using Comsol?
Yes, definitely. I mean, that's a typical multiphysics application that we are good at. So that involves electromagnetic analysis and structural analysis.
Okay, great. Another question, how did you specify the speed of the billet?
Well, we solved the heat transfer as a stationary problem, but that still allows us to add a convective term in the heat transfer. So essentially we model that as a convective term in the heat transfer in the billet, meaning that the heat will be dragged along with the motion of the billet. So it's straightforward.
Okay, great. Another question about the billet. The billet conductivity will affect skin effect. How does the model handle this and factor in reduced conductivity at the high temperature?
What you typically do is that you introduce the temperature dependency on the conductivity, and in this particular model we can use, for instance, a linearized resistivity model, or we can use empirical data in the form of a lookup table. Comsol can easily import from Excel or from text files lookup tables for various physics parameters. So once you have that dependency tabulated or in the form of a polynomial or linearized function, it's easy to introduce that into Comsol Multiphysics.
Okay, great. Another question, do you include inductor nonlinearity in the analysis, and what types of nonlinearity are treated?
Typically, as we showed in the E-core transformer model, you can include saturation effects. You can also introduce hysteresis effects, but that's a little bit more elaborate. But we have examples on how to do that as well. But I would say pretty much standard saturation effects are introduced by the use of empirical data, real magnetization curves that you specify using interpolation tables. And there are, we ship some data for nonlinear materials as examples with the product, but it's very easy to import your own stuff from a text file or from an Excel file or wherever data source you have.
Okay, great. Does the inductive heating model include Joule heating equations to compute the heating?
Yes, I mean what we use is essentially the resistive losses due to induced eddy currents in the billet.
Okay. How is homogenization performed for coils and materials? Many homogenization formulas exist, and which ones use Comsol?
I think I showed a little bit of that when I discussed the multi-turn coil domain. which essentially just says I have like a flat density of wires over the cross-section of the coil. So I just take the number of wires, multiply by the current in the wire, and spread that out across the cross-section. I compute the induced EMF the same way, integrate over the volume, and multiply by the number of wires. So that's one example. When it comes to material modeling, we also have models for like mixture models and well, what we call porous media models that can handle mixtures containing small grains of different materials in an averaging sense, and there are several ways of dealing with that. So you can handle anything really from series connections between the different material particles to parallel connection and power laws handling the in-between. So you have a lot of options there that are pre-cooked for you.
Okay, great. Another question: how is the material orientation introduced to the model? Anisotropic magnetization, for example. Is it with tensor-like material properties, with direction vector normal to the magnetization axis?
We typically have tensor-like material properties. We also have some pretty neat tricks to compute the coordinate systems following materials that can be used to model more fancy shaped iron laminated cores, for instance.
Okay, great. Is there a scripting interface in Comsol that could be used to simulate multiple variants of a product in an automated fashion?
Yes, we have a connection with MATLAB. So essentially, if you use the live link from for MATLAB, you can run your Comsol model from within the MATLAB environment. We also have possibilities to run Comsol with Excel, with the live link for Excel as a front end. And then there is also a Java API that you can work from, so to do more advanced programming and scripting and programming language control of the simulation process.
Okay. Is the software capable of modeling multi-phase transformers?
Yes. You can essentially have, like any number of phases, and you can specify phase angle for a conductor and for a coil pretty arbitrarily. It doesn't really have to be three-phase system. It can be more or less anything.
Okay. Can models from different 3D software, i.e. Inventor, be imported into Comsol?
Yeah, I mean, definitely. I mean, we have CAD interoperability with all the major CAD vendors. So, and that can be done either via the live link products, which set up, like you have both products running and establish a link between. So the Comsol will see the geometry in the CAD package, and when that changes, Comsol will recognize the change and update accordingly. Or you can use file-based CAD import.
Okay, great. Is it possible to run heat transfer and electromagnetic on the same model transformer at the same time?
Oh yes, sure you can do that, and we have various approaches to doing that. I mean, you can run everything in the time domain. You can run, for instance, in many cases there is not much action going on in the heat transfer part during one electromagnetic cycle, so very often it makes sense to do as I did for the Billet model, that I solved the electromagnetic part as a frequency domain simulation, and then I can run the heat transfer part either stationary or time dependent. And then I introduce just the heat source in the heat transfer part will just be a cycle average heat source. But sometimes it makes sense to solve fully coupled in the time domain and see cycle variations in temperatures and heat source. It depends a little bit on the time scale of the device.
Okay. What output in terms of lumped parameters is available from a simulation?
For electromagnetic simulations, we typically output impedance. For static analysis, you can get resistance matrices, capacitance matrices, inductance matrices. For frequency domain, it's I would say it's typically impedance, and you can even get S parameters, for instance, for like RF MEMS devices and those type of applications.
Okay, great. Is it possible to model resonant RF coils?
Yes, that's something you can do both in the AC/DC module and in the RF module. Yeah, definitely, and we have one introductory example to the AC/DC module showing you how to model a resonating coil.
Okay, I think we have time for maybe one or two more questions. Can shielding be metallic enclosures? Can shielding by metallic enclosures be handled?
Yes, I mean shielding of metallic enclosures is typically a fairly challenging problem, but we have special boundary conditions allowing you to handle even geometrically thin walls just as a boundary condition, mimicking the partial penetration of the fields through the enclosure.
Okay. I think we're going to wrap it up there for the questions. Thank you again, Magnus, for your presentation and answering all of these questions from the audience. A question that we often get in these Comsol webinars is about how do they try out Comsol Multiphysics. Well, you can go to a workshop. And at a workshop is a free hands-on event where you can meet a Comsol specialist and try Comsol Multiphysics with his or her help. And here on the slide in front of you now are some of the workshops and locations. If you use the link that's provided there, you can get more detailed information on where to go to those workshops. Now, also, if you can contact Comsol directly, and there's a lot of information that's available about Multiphysics and Comsol and their products on their website, and you can find user stories, a model gallery, discussion forum, and a lot more. So you can, again, use the URL there, www.comsol.com/contact, and I think we'll wrap it up right there. So as I indicated earlier, this session will be archived in about 24 hours on www.spectrum.ieee.org/webinar. And once the archived webinar is available, a notification email will be sent to all the registrants. I'd like to thank our presenters today for making this such an informative hour, our sponsor, and thank you, our audience, for participating in today's session. We hope you found today's event valuable and will return for future IEEE Spectrum webcasts. Thank you.